Okay, alrighty. Let's get into Desmos here and see if we can construct some waves and demonstrate the beat frequency that you did using other software. Let's start by graphing a basic sinusoidal wave. We're just going to write y equals sine t. There's our sine wave. But our sine wave has a problem. It's based on pi, and so it's crossing at really weird values on the axis. It's crossing at pi right here and 2 pi right there, and that's kind of annoying. I'm not going to improve things by doing this. By writing 2 pi in there, I've now forced it to complete a wave in a single unit of time. So when t is equal to 1, a single wave has formed. That's nice in the sense that by putting the 2 pi in there, I'm forcing a zero crossing right here. One complete wave in 1 second. And that gives us a little bit of power. The cat. It's the cat. She's sneaking up on me. Okay, she stopped. Anyway, it's crossing at 1. I don't want to have it cross at 1. I want it to cross 440 times a second. Why? Because that's middle A. So once we establish a single sine wave lasting 1 second on this axis by simply writing in 2 pi, we can cause it to deliberately cycle 440 times in that. And think about it. If a single event of 2 pi triggered when t is equal to 1, if I just multiply it all by 440, we should be good. But let's make it like this and put the 2 pi in brackets. So I'm going to make outer brackets first on the sine, and then I'm going to go in here and I'm going to put in 440. And lo and behold, we now have a giant red bar. And if I was a famous enough artist, I could hang this in the National Gallery and get paid millions for it. If you don't believe me, look up The Voice of Fire. What on earth has happened to our graph? Well, 1 second on our graph, as my laggy computer backs out, is only 2 of these large boxes here. So that wave went up and down 440 times in that mess. So there really is a wave there, but you're going to have to zoom in a colossal amount to see those 440 pulses. So we need to do something to shrink it. Because trust me, you'll be zooming in for a while and you will see those waves. Just the graphing density is so high you can't see it. It's like that, even crazier. The height of the graph is 440 times higher than it is wide. That's why you can't see it. So if we smoosh the graph downwards in physical height, then we might see those waves. So I'm going to put a smushiness here, 0.001. Where did it go? It is still there. If you ever lose your graph, just hit the home key. And it's there. It still looks like a red line, but let's zoom in now. I've really squooshed it down vertically. And if we go in, I'm getting closer, I'm getting closer. Well, looky here. Now that I've flattened the line, we can clearly see the oscillations, the wiggly up and down. I'm recording a lesson. Not just talking to myself like some people do. Anyway, there's the wiggliness of this wave, okay? But I would like to take that wiggliness and get it the heck out of there. It's on my axis and I want it for something else. So you see the decimal 01? That would be a great place to shove this wave. So let's go in here and go plus decimal 01. No, I've done it in the wrong spot. Ooh. Plus decimal 01. There we go. It's shoved up out of the way. But I want a second wave to play with. It needs company. So I'm going to go here and go duplicate. Now, why can't we see the second wave? Because it's sitting on top of the first one. Where do you expect it to go? The cat. She's on the move again. I know she's eyeing my shoulders. Okay, I'm going to... Stop it. Decimal 006 will be a good place for our second wave. There we go. Okay, so there's the second wave. Now, since I made the first wave 440 hertz, what if I make the second wave 445 hertz? Okay, it's slightly changed. You can't really see it, but it's definitely drifting off the first wave. Not by much, but it most certainly is. If you don't believe me, you see out here? Look at where it is there and how much the point is drifted. It's very tiny. Now what we're going to do is put these together. So once again, be lazy. How often do you get a teacher telling you to be lazy? I'm going to make the summation of these two waves. Come on, old and slow computer. There we go. And I'm going to put these two waves on top of each other. All right? Except, I don't want them stacked way up in the air. So we're going to take off these offsets on the vertical. Okay? I'm going to go in here. Yeah, and the second one didn't come over anyway. So there, no, where is it? It's off screen here. There she is. We'll take off that other little bump up. Now, the addition of the two waves is sitting nice and neatly on the axis. So this is what you get when you add them up. Now let's start backing away and see what happens. Wait a minute. Look at that. They're big and fat right here, and then they completely cancel out right over here at 0.1 on our axis. So let's zoom in, and sure enough, look what's going on there. Almost complete destructive interference. You know, destructive interference, that's like when a girl is working really well on her project and the boys stick their noses in and the project is destructed. In this case, it's a 0-0 lineup. That's why the wave canceled. But you'll find others where it's negative meets positive. You see right here? The low spot meets the high spot. The hump meets the dump. My hump, my love you sinusoidal hump. Okay, so we're going to back out here. But this squishiness has really made it hard to see that going on in there. So let's take these guys and really get them the heck out of the way. I'm going to slide the original waves way up here to like 0.06. So I'm going to go in there and just take out a 0. Up it went. How do you like those effects, eh? Years in training to go. And now I've taken my original two waves and I've shoved them way off out of the picture. We're just looking at the composite now. And I'm going to unsquishify it a bit. I'm going to take away this really tiny multiplier, and we're going to stretch it. Oh, 10 times higher than it was before. Look at those waves. There's a time off the coast of New England years ago. I saw waves like this. I need some Perrier from doing my pirate voice. Okay, now we're starting to see a little bit of squishiness and not squishiness. Oops, looky what I forgot to do. Remember, we're multiplying two waves. That's why I just kind of like, let's like take one off here, 2. That's better. The sea should be rough today than quiet. Can't do it. Anyway, you get the idea? Now we clearly have a zone of completely destructive interference and completely constructive. All I had to do was play with the squishiness and the frequency to get this. Now we have one slight other problem. I would really like it if this 0 crossing here at 0.1 was way back over here at the 0. And then you guys will be able to count beat frequency really easily. You know, like it's got the beat, man. It's beat frequency. Yeah, let's snap the fingers, man. Okay, so what do we have to do to shift a graph left or right? Remember math class? All you have to do is add something to the x, in this case the letter t. So we're about to go with more brackets. So I'm going to put a bracket near the T, and I'm going to subtract 0.1 or add 0.1. Let's try taking away a 0.1, shall we? And we've got to do it on both of these equations here. So, over there, Squidward, he'd be taking away a 0.1. Oh no, that's not 0.1. 0.1. That should, there we go. We've got our axes lined up. Our battle axes. Now, it looks kind of hellish at first, but we've simply set up a circular wave, a sine wave, that will complete itself 440 times when the unit number 1 is reached. And then we nudged it down, we squishified it a little bit, but now, guaranteed, we can pretend, well, not pretend, it is. The time axis is now exactly seconds. So how many beats would you hear? If you played this, you would hear wah, 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 and you will play it. It won't sound like me going wah, 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 wah. It'll be the computer doing it. But let's take a look. 1, 2, 3, 5 beats in 1 second. Well, that would be a frequency of 5 beats per second. So the beat frequency is a 1, a 2, a 3, a 4, a 5 in 1 second. So what you're going to do, I just did one of that thing again. Curses. The screen of death. Will she come back? Captain, the power's back online. Okay. Now we've got 5 beats per second. What are you going to have to do? You are going to change the starting frequency and the end frequency. So after we set this up together, all you have to do is go in here and change this to the numbers I suggested on the assignment and count the beats. And then you will compare them to what you heard using those annoying sound oscillators I found for you on the internet. So I'll do another one, not one that you're supposed to do. I will do an example that won't count. What if I put in 460 here? It's a pearl necklace. So then we try to zoom in for 1 second if we can find it now. There it is. There it is. See, there's our 1 second. But oh my gosh, my old man eyes won't let me see all the way to 0. Maybe. I'll zoom out here. Oops, it didn't cross at 0. I've bumped something. What did I bump? I changed a number here by mistake. Nope, they're still good. It drifted for some reason. But anyway, you could count along to the 1 second mark and get your frequency. But you're only going to be swinging these between 430 and 450, okay? So, and obviously, if you put 440 in there, there is no beat frequency. It'll just turn right back to a plain old, unaltered wave like that. But the minute you don't have the two waves share the same frequency, you should start to see beats appear. And then you will easily be able to count those beats and how many occurred per second. Okay? Sounds good? Off you go.